Hey Elixir friends, I'm Andrea. I'm a member of the core team of the Elixir programming language, and this is the first video of a series I'm starting on solving some network programming challenges in Elixir. The idea is to solve the problems on protohackers.com, which is a website that I recently came across and learned networking in Elixir along the way. Protohackers, this website, is kind of like Advent of Code, if you've heard about that, but for network challenges. In this video, we'll start with the first challenge on the website, which is setting up a sort of a smoke test to make sure that everything is wired up correctly. And we'll implement the TCP echo server, which just spits out anything you send to it over TCP. Before we get started, one disclaimer: you'll need to understand Elixir syntax and semantics, or at least be familiar with those. There are a ton of great resources out there. First and foremost, Elixir's own website, which is linked in the description below. So go check those out if you're still learning Elixir. So, okay, let's get rolling. So the idea behind the smoke test that we'll start with is described here. You can visit this, it's linked in the description below. And it's just about essentially accepting TCP connections. Whenever we receive data from a client, just send the data back unmodified, and just like handle binary data, and that's pretty much it. So it's also described in an RFC, as you can read here, and Protohackers provides this way of checking what you implemented. So you need to host your server somewhere at an IP address and a port number essentially, and we'll use fly.io, a free account on fly.io to do that. And I'll show you in a later part of the video. So let's get started with setup. Okay, so let's start with building our TCP echo server locally before moving to the deploy steps. The first thing we'll do is make sure that I'm using the right Elixir version. So I used ASTF to manage my Elixir versions, and I'm gonna just set the version to the latest published Elixir version, and then I'm going to check that that works. Awesome. Okay, now we'll create a new project. I'm gonna go with Protohackers. I'm gonna pass the --sup, which stands for supervisor flag. I'm using this flag to scaffold the supervision tree. The idea is that this command will generate an application file with a start callback, put the skeleton of a supervision tree in it, and hook it up to start in mix.exs. So I'm gonna just say code Protohackers, and we'll have another window here. There you go. And so you can see that there's a file here called Protohackers application, which contains the scaffolding for an application callback and the supervision tree, and then mix.exs contains what's needed to actually start the application. Okay, let's just make sure that everything is wired up correctly. So I'm going to open a shell in here, and I'm going to just write mix test to make sure that everything gets compiled, tests are passing, everything is looking good. Awesome. All right, we're almost ready to write our echo server. First, let's just quickly go over the application's architecture. And I won't be talking in depth about what TCP is or how the protocol works, what sockets are, and so on. You'll find resources to all of this stuff in the description below. If you're not familiar with these things, I recommend going over those and then coming back here. So the idea is this: we want a server that listens on a port that we decide and accepts a TCP connection, then reads the data sent by the client on that connection, sends that same data back to the client as a response, and then closes that connection. For now, we won't really worry about concurrent connections. Let's get started with one connection at a time, so accepting one connection at a time. So to start, we'll want to create a long-lived process that acts as the server. We'll go with a gen server, even if we won't use most of the features that gen server provides. So let's create a new file, which we're going to call protohackers/echo server.ex. And then we're going to open that file, and we're going to just write the dev module protohackers.echo server, and we're just going to write use gen server in here. Cool. Okay, so we'll start with a startLink function that the supervisor will call to start this gen server as its child. Yes, as you can see, Copilot is trying to help here. but in this case, I'll just want to start this and I'll pass no state to it because we won't really be using a state. And I also like to match on empty options so that we make sure that this doesn't get accidentally started with some random options. Awesome. So we don't really care about passing a state to the init callback, but we do care about storing some state for the server. As a soft rule, I almost always tend to use a struct for the state of a gen server, since it takes away a whole class of kind of quote-unquote type problems. So trust me for a sec on the field that we'll put in here, but we're gonna go with def struct listen socket. Okay, and then we go with the init callback for the gen server. So we're gonna say init, no state, okay, and we'll say that this is an implementation. Okay, so in this callback, we'll initialize the state of the gen server. For now, we'll just say logger.info starting echo server. We'll also have to require logger to do that. And we'll return the empty state. So there it is. Now we will hook this up in the application file under the supervision tree. So we will put it as a child of our supervision tree, protohackers.echo server. Perfect. And we're going to try to run this thing. So I'm going to do mix run -- no halt so that it doesn't just stop. And it says starting echo server. So everything seems to be wired up correctly. Okay, we're ready to accept a TCP connection. So the way that TCP servers work is that you usually have a thing called the listen socket. That's what you bind to a port on your machine. In order to accept connections from clients, TCP libraries usually provide something called accept or something like that. When a listen socket accepts a connection, it returns a peer socket, which represents that one-to-one connection between our server and the connected client. A listen socket can accept many connections, but a peer socket is always one-to-one. So we'll create a listen socket in our init callback in the echo server, and GenTCP, which is the TCP library built into Erlang and OTP, provides just what we need, which is gentcp.listen. So let's write this down. What we're going to do is we're going to pass down some listen options that we're going to fill in a second, and then we're going to call gentcp.listen. We'll pick a port. I'll go with 5001, why not? And we'll pass the listen options. And this can return either OK and a listen socket. And in that case, we are going to actually initialize the state to with that listen socket, and we're going to return it. Or this returns an error with a reason. In that case, for now, we'll just stop the server. There's no reason to try to keep listening here. We'll just blow up and stop the gen server. For the listen options, we'll go with mode binary. This one says that the data sent and received on the socket should be represented as binaries. This is more of a legacy thing in the Beam. It's great to know when you're doing network programming in Elixir, but since the default data in the Beam is usually represented as chart lists, especially they're kind of falling out of fashion. So especially older pieces of code, but GenTCP by default works with chart lists. So if we say mode binary, then all message exchanges, all data written and read from the socket is going to be binaries, which is what we want. It makes a lot of things simpler. Then we're going to say active false. We don't need to worry about this too much, but this option says that all the actions on the socket need to be explicit and blocking. So we'll go over this in future videos, but for now, this only means that there will be no Erlang messages flying around in our programs. And then the last option is reuse add res, which is going to say true. This is just a quirk. Don't worry too much about it. It just says that we can run our tests, run a program, and reuse the same port number. So it's just we're not going to worry about this too much. Okay, so our server is now listening on port 5001. We're actually going to move this log over here and say starting echo server on port 5001. Okay, the server is not really doing anything at this point. We can try to run this. It's going to say that it's listening on port 5001, but it's not really doing anything. So let's accept the connection. To do that, we'll use the continue feature of Gen Server so that we can finish the initialization right after starting the listen socket, so right about here. And then we can start accepting connections asynchronously so that the supervisor can keep starting other children. So we're, instead of returning OK state, we'll just return OK state and then a tuple that says continue, and then any term. We'll say accept over here, and then we'll define a handle continue callback, where we'll match on the accept atom as the first term, and then we'll match the state as the second term. We'll have to say imp here too, to say that this is a Gen Server callback. And in this callback, what we'll do is that we'll accept a connection, we will deal with it, and then we'll go back to accepting a new connection. If we can't accept connection, it means that something is broken. For now, we'll just shut down the server. And the supervisor will start it back up anyways. That's kind of the beauty of OTP. So we'll use the function gentcp.accept, which takes this listen socket and doesn't take any other argument. And it returns either a one-to-one socket that I mentioned earlier. And in this case, we will handle the connection, which we'll write in a second. And then we will just keep going. So essentially, we will return no reply, and then again continue accept, which is just gonna call handle continue again, essentially. And if accepting a new connection fails, we'll just blow up the error and stop the Gen Server by doing stop reason. Cool. So now we have a chance to write some helpers, and the only one we'll write is handle connection, which takes a socket. And so now we handle the connection. The Protohackers problem description says that we have to receive the data until the client closes the socket. So we will use some recursion since we don't know when to stop reading data. So we'll just write a function for now that doesn't exist, which is receive until closed, and we'll pass the socket and we'll pass the buffer. I really like to use underscore named variables, which don't really do anything except tell me what this value is. So it's much easier to read in my opinion. And we're gonna say, okay, data. So if we get, this is the return value that we'll decide, I'm gonna say gentcp.send socket data. So we'll send the data back. Error reason, we'll just log the error. We don't want, and we'll wanna say something like fail to receive data, and we'll inspect the reason. We don't really want to stop here because a broken connection, we don't want a broken connection, a problem with a single connection to stop the whole server. We want it to just, essentially ignore it. And after we've done either of those actions, we can close the socket with gentcp.close socket. One thing I want to mention here, gentcp.send, this is the function that you use to write the data to the socket. And for now, we'll just not really talk too much about it. It's just going to send the data back on the socket. In future videos, we might dig deeper into what that does and how it does it. But for now, let's write the other function, which is receive until closed, the recursive function, which takes a socket and it takes a buffer. And what we do here is we say, okay, gentcp.receive. And this function is the function that reads data out of the socket in active false mode, which for now we don't really have to worry about. It just blocks until there's data to be read from the socket. We pass 0 as the second argument. The second argument is the number of bytes to read. 0 means just read all available bytes. And then we pass the timeout. We're going to go with like 10 seconds. It's a timeout in milliseconds. And the idea here is that we want to use the timeout because otherwise our server could potentially just be stuck waiting forever. So this can return OK data. And if it returns OK data, then we can just keep recursing. So we're going to say receive until closed, socket, and we use buffer data. What I'm using here is, instead of concatenating the two binaries, is using IO data, which is a widely used tree-like Erlang data structure that allows to put in there binaries and integers that represent bytes and nested binaries and nested lists of binaries and so on. And it allows us to avoid unnecessary memory allocations that would happen if we keep concatenating binaries just to end up with a final binary anyways at the end. We could convert this IO data to a binary when returning it from this function. But the nice thing is that most write-centric APIs, such as GenTCP or file-based APIs in Elixir and Erlang, support IO data natively and write very efficiently to operating system buffers. So in this case, we can simply write the IO data to the socket with gentcp.send. So gentcp.send takes, as you can see in the type spec here, the packet that you can send is IO data. The type is IO data, so it's just going to work. So if we get the data, we concatenate it to the existing buffer. If we get an error and the reason is closed, which means that the socket was closed, then we can return the buffer, which shows the whole data that we got until now. In order for this to work in Erlang, I recently discovered that we need an additional option with starting the listen socket. And that option is called exit on close. So I'll just add it over here, exit on close false. Without this option, we wouldn't be able to write to a closed socket, which is what we want to do, because in this case, what's happening is that the client is closing its write side of the socket, but it's our read side of the socket is closed, right? But our write side of the socket is still open, so we can still write to the socket, and the client can still read from that socket, which is exactly what we want to do. So with that option necessary for this to work. And the last part is just doing any other error, which would just bubble up to our caller. So that's the whole function. And now, where would we even show up without tests at this point, right? So it's a good time to start writing some tests. And you might have noticed that I didn't take a test-driven approach, and I generally leave writing tests with writing software. I'm not very religious about TDD, but to each their own. In any case, the first test I'd realistically do when working on something like this is just some manual testing. So I would start the server over here. I had to move my head around, and I will start another terminal over here. And what I would do is just use something like netcat, which is built in here. And I would do something like echo foo, and I would netcat it to localhost 5001. And I get foo back. And I had to do a quick cut over here because I forgot to return the state from handle continue. So this was not really handling multiple calls. But now that I cut and I fixed that, we can do exactly the same thing and that we were doing before. And I just say, you know, whatever I send is going to be returned from the server. It's going to be echoed back. So this seems to work. Let's write a proper automated test now. I call this an integration test because we'll simulate a client connecting to a server. So what we'll do is create a directory, test Protohackers, and then we will create a file in there. So test Protohackers echo server.test.exs. We're going to open this file and we're just going to write a little test here. So protohackers.echo server test, and we call use xunit.case. Perfect. And we're going to say test echoes anything back. Awesome. And so what we're going to do is we're going to we know that the server is started by the supervision tree of our application. So the server is kind of already running here. And what we're going to do is we're going to use the GenTCP module to just behave as a client. So we're going to say, okay, socket equals gentcp.connect, and we're going to say localhost, and the port is going to be 5001, and there's going to be the only option is going to be here, it's going to be binary, mode binary, and active false. Great. And then we're going to say assert that gentcp.send socket foo equals okay. So no problems here. We shouldn't get anything back yet because we're not closing the socket. So I'm just going to copy these and I'm going to say bar. And then at this point, I can say gentcp.shutdown. I can use this function to shut down only one side of the socket. I should call this socket, I'm sorry. I can only shut down one side of the socket, in this case our right side, and this is gonna show up as, so I can still read from the socket, which is exactly what I want. And now I can write my assertion, which is assert that gen tcp.receive all available bytes from the socket with a timeout of 5 seconds. For us, it's gonna be equal to okay foobar. So all the data that I sent until this point. If I try to run mix test now, yep, we see that this passes. We have 2 tests now instead of 1, so this is working. Awesome. Okay, now let's talk about a vulnerability that is in here. Can you spot the vulnerability with our server here? Aside from denial of service attacks, which are always kind of a problem that we're not going to go into right now, the biggest one here is that we just received data indefinitely. So this piece of code is essentially a potential memory leak and a potential memory attack, right? An attacker could just send data without ever closing the socket, and they probably use up all the memory available to the beam, because we'll just keep growing this buffer indefinitely. The fix is not really hard. We just set a limit on the amount of data that we can buffer, and we'll just return an error if the data is too much. So we'll just create a little module attribute here called limit, which is going to be like, I don't know, 10 kilobytes maybe, and say that this is, or like, let's make it 100 kilobytes. We can afford that. And this is like 1024 bytes times 100 for 100 kilobytes. And we're going to say that this function also now takes a buffered size, which is what we buffered till now, which is going to pass here. Buffered size is 0. We're going to start with 0. And then we're going to change this slightly to say that if we receive okay data, but the buffered size plus the byte size of the new data is greater than limit, then in this case we just return an error that says something like buffer overflow. And if we get data instead, it means that we're still not over the buffer, so we just do this, but we change the recursive call to be buffer size plus byte size data, so we update the buffered size. We also want to write, so this should just be it to solve this. We can write a test because that's a pretty important feature that we want to make sure it just works. So we're going to say echo server has a max buffer size, and we'll copy the first line from here. And then we're going to say assert that gen tcp.send to the socket, and we're going to send just slightly more data than we can afford. So we'll use the binary.copy function, which just takes a binary and copies it over as many times as needed. We're going to use 1 kilobyte times 100 plus 1, which is exactly what should trigger our problem. And in this case, we're going to write a test that says assert that gen tcp.receive socket all available bytes is actually going to return an error, which is error closed. And I forgot to say that this should be equal to okay. So we can send, but the socket is going to be closed by the server essentially. And if I try to run mix test over here, yep, we got the log here. And the test is passing. We're not going to care about the log too much for now. We're just going to leave it there. We could clean it up in tests, but I feel like that's okay to have. Okay, so the last part of the problem that we still haven't solved is that the problem mentions that we need to be able to handle at least 5 simultaneous clients. Right now, that wouldn't work. So if we get 5 clients in parallel, 4 out of 5 would just be waiting for the first one to continue. Because we are handling connections sequentially, right? So we'll have to do a little change in architecture in order to support concurrent connections. And the change in architecture will be essentially this. We'll spawn a new process to handle each connection in the background whenever we accept a new client. So that's all will change. So Elixir comes with just the right tool for the job, which is task.supervisor. And with task.supervisor, we can dynamically spawn supervised tasks pretty easily. We can also set a limit on how many tasks can be running under the supervisor at any given time, which will essentially act as our concurrency limit. A task is really a nice choice here because handling a connection is an isolated little world. It doesn't need to communicate with anyone else. It doesn't need to communicate with other processes. The handling of a connection is really isolated. So we don't care, and we don't care about the result of handling a connection. We don't care about how it went. We just want to handle it and then be done with it. So the changes that we need are two. To start the supervisor when starting the echo server, we want to start that task.supervisor. And we'll do that by calling over here just when initializing the echo server. We'll say, okay, supervisor equals task.supervisor.start link, and we'll pass the option max children, and we're going to say something like 100 maximum children. We could say 5 just to comply with the problem, but 100 is super fine. And then we're going to add this supervisor to the state of this Gen server. So we're going to add a field to the struct here. And when creating the state here, I'm going to say supervisor equals supervisor. Okay, so the supervisor is now running when we start the echo server. And now on to spawning tasks. And that's just a matter of changing the call to handle connection, which instead of being here, which just executes sequentially and blocks until it returns, let's change this line to actually be task.supervisor.startChild on the state.supervisor. So that's task supervisor we'll use. And we'll just pass this as a function, as an anonymous function. And that should be it. If I try to run tests again, they still pass. I can write another test that kind of tries this out, and we can say test handles multiple concurrent connections. And I can use tasks again here. So I can say, for example, spawn 2 or 3 tasks. And for all of them, I can say task async, and I'll pass a function here. And in that function, I'll do exactly what this test is doing, essentially. I will do exactly the same thing. So I'll create a socket by connecting to the server. I'll send some data. I'll shut down its write side, and then I'll make sure that the data is echoed back. And after I spawn these tasks, I'm gonna wait for each of those. So I'm gonna say for each task, I'm gonna call the task.await function. I don't really care about the result because these are just gonna blow up if something is broken here. Okay, and I realized I just had a typo over here. So let's try to run the tests, and they pass. So everything is going fantastic. Okay, I think we're ready to deploy. So let's take a short detour about that. Okay, so this video was the first chance I had to really try out Fly.io, and I'm super impressed. It works fantastic for this particular use case. The base plan is free for everyone, so you can just go ahead and create an account on Fly.io, and I'll see you here when you're done for following along if you want. For now, I'm just gonna go to my dashboard, and you'll see that I have some applications running. I have a trial plan, and so I'm just trying this out essentially. Okay, so to make our app deployable on Fly, we'll start by initializing the release setup with mix release.init. And Fly has really great documentation for deploying Elixir apps, and which is linked in the description below. For example, they tell you to add a bunch of stuff to the amp.sh file, which will just essentially, I will just copy paste in here. So I'm copying it from my notes over here. Okay, and I will just put it in here. I'll just replace all of this with what they tell you to put in here for their internal IPv6 networking and stuff like that. So now it's time to create a Docker file to deploy the application. Docker file. I will just, so once again, Fly really points you to the right direction and it gives you an example Docker file. Their example, however, assumes that you want to run Phoenix, which we don't really want to do in this case. And we can keep things slightly simpler in this case. So I have the file the Docker file ready to copy paste over here. So I will just do exactly that by going to Docker file and just pasting the contents over here. We can walk through this real quick. It's just taking a builder image that we'll use to build the release, and then a runner image that we'll use to actually copy the release over and then run it when we need to run it. And the builder image is just installing a bunch of standard stuff on Debian over here. It's installing hex, rebar, it's downloading dependencies, compiling them, it's compiling the release, it's generating the release itself, and then it's installing a bunch of stuff in the runner container, and then setting a bunch of options, and then copying the release and starting. So that's pretty much it. Okay, so we're kind of ready to go. We're almost there. What we want to do here now is we want to we want to use the Fly CLI to actually bootstrap this application essentially, so you can download this. Okay, so let's try to launch this. I'm going to do flyctl launch. It's going to ask me a few questions. Create a Docker ignore file. Not really. Choose an app name. I'm going to call this Protohackers in Elixir. Okay, I'm going to go with Frankfurt. Sure, sounds good. Would you like to set up a Postgres database? No, thank you. Not even a Redis database. And would you like to deploy now? I'm going to say no, because I need to do some changes to our Fly configuration. So as you can see, this created a fly.toml configuration file. And if I open this, there's a bunch of stuff in here. We don't really care about the most of this. One thing that I'm going to do is, according to the Fly documentation, we want to change this to sigterm, because that's what the beam uses to shut down gracefully. So the kill signal is going to be sigterm for when we deploy, essentially. And then we need to open our 5001 port. So here you can see that there's a bunch of ports for HTTP and HTTPS that are open. I want to get rid of those because we're not going to be using these. I'm going to be saying that the internal port is 5001, and then I'm going to say that services.ports, I'm going to add the port, no handlers, and I'm going to say that the port that we want is 5001. Okay, this should be good. So we're almost ready to go. We want to now deploy with flyctl deploy. And I'm going to skip ahead while this deploys, so I'll see you in a second. Okay, so it finished deploying, and after a bunch of painful time spent on this in the past few days, I discovered that Fly doesn't really support custom ports on shared IPs, which is what you get by default. It's a shared IP. However, we have one free allocated IP that we can use on the base plan. So to allocate that, we just do flyctl IPs allocate v4. And it's going to think for a second, and then it's going to spit out a IP that we can use to test things out for our server. That's the IP. So what we're going to do is we're going to say echo foo, and we're going to use netcat again to spit this out on 5001. As you can see, it works. It still works with everything. So now, last but not least, it's time to go back to our Protohackers challenge and check if we actually made it. Okay, so here we are on the smoke test challenge. As you can see, I already solved this, yes, while trying this out, but we're just going to pretend I didn't, and we just paste in the IP address, paste in the port number, and we are good to check. Let's see how it goes. It's thinking, and it says, I tried this, I tried that, everything passes. So we made it. So we went through a bunch of stuff. Now we have a working TCP echo server that actually any of you can ping and try out. Pretty please don't try to find vulnerabilities or to perform denial of service attacks. This is out in the open, so you could, but just please don't do that. So this is the first video of a series that I'm doing on network programming in Elixir by solving this Protohackers challenge. Stay tuned for the next ones, where we'll keep solving just the next challenges on Protohackers. There's 9 of them currently, so we're bound to have some fun, and see you next time.